that can only needs 50 instructions, a high-level change, then your energy delay product decreases by what? 1/4, right? If this is 50 and this is 50, then compared to the previous algorithm, it decreases by 1/4. Okay? So a lot of the changes, a lot of the impact comes at the high level. Okay? So once you have a 1/4 of the solution, you can use a much slower, lower power processor, less expensive processor, et cetera, et cetera. Okay? Now, so what we'll do next is we'll look at parallelism and pipelining as a way to rethink how things done at architectural level. But I guess it's more circuit, it's more hardware concentration. Hopefully you'll get an idea of what I'm talking about, okay? But the point that you want to take home is that a lot of the changes come at an architectural level, algorithm level, has a strong impact. So let's look at some of the simple examples, okay? So, consider this problem. This, by the way, is a paper, it's a classic paper. It's a 1992 paper from Chandra-Prasad. It's the second most downloaded paper in Solid State Journal. So here's an example. This data path consists of an adder. This is an adder. And a comparator. And you have, these are 8-bit, so these are flip-flops. There's 8 of them here, 8 of them, 8 of them here. So you're doing a simple data path. You're basically sampling the bits A and B, right, which are 8-bit wide, adding them, and then comparing them to find out, you know, which one is larger. Okay? This is your layout of this data path. Okay? You're told, so they do this layout. This is fabricated in the technology, and then your delay from here, your adder delay, plus your comparator delay, is about 25 nanoseconds. So this can run at roughly 40 megahertz. Okay? Let's say the total capacitance that is being switched is, we call that C reference. The supply voltage is 5 volts. So then the power dissipation is what? C ref, right? F ref times V ref squared. Okay? So that's your power dissipation for the circuit. Now, what can we do architecturally to, you know, improve performance? All right, that's what we're going to do. So this is your basic example. Now, parallelism. Okay, one thing that you could do. Okay, you could basically double the data path. Again, this shows a layout of the area. So now you have 2 of them, adder, comparator, but as a result of doing 2, and then at the end you put in mux. Because now you have 2 of them, and if you want to maintain the same throughput, what do you have to do? Right? Because now both of them are doing the same thing, what you can do is that you can decrease the frequency by 1/2, right? Instead of sampling this every t seconds, you can sample it at every, what, 2t seconds, correct? Now, while this is working, this is also working, so you basically, but this mux is sampled at 1/t. So basically it's it's like a ping pong. It takes the result from this side and then it takes the result from that side and so forth. Do you understand? But each data path has now twice the time. Now because I have twice the time, what can I do? Lower power, but how? Lower the supply voltage. Now I have all the time twice the time, so I can decrease the supply voltage so that it doesn't finish early. Remember, I don't want to finish early. I want to finish just at 2t. So because now I have twice the time, I decrease the supply voltage. I decrease the supply voltage and see what happens. So in this particular example, F parallel is the frequency that this is running at. It's 1/2 of the reference, right? V parallel, the supply voltage, as it turns out, they can decrease it by almost 2 by 1.7. Okay? Now what happens to C parallel? This total switch capacitance. Obviously it's going to double, right? As it turns out, it doubles by roughly 2.15 of C reference. Not quite, it's a little bit more because there's more interconnect you can see here, and then there's this guy. So now if you do this, the power dissipation of the parallel circuit is 2.15 times C ref, B ref squared, B ref over 1.7 squared. Now the frequency is lower by 1/2. And if you do that, this gives you 0.36 of P reference. So there's a 64% decrease, reduction in power dissipation, while maintaining the same performance. Okay? So this is a architectural decision. Yeah.
Why did you replace the variable just because everything is twice? I didn't understand that.
So what we've been talking about, so the trick about low power is to never finish early. So if you can, so it's like running, or if I tell you you have 1 minute to go from here to there, and I ask you expend the least amount of energy, then you will just walk extremely slowly and get there in 1 minute. Why run? Because you still have to wait for 1 minute at the door. The same thing here. If you have more time, the trick to low power is that you want to finish the computations right when you need it. So you want to basically intentionally increase the delay. How do you increase the delay? By decreasing the supply voltage. Once you decrease the supply voltage, your energy decreases. Right? Any questions? So this is 64% reduction in power dissipation. Not bad, no? Let's do another example. Pipeline data path. Okay, in pipelining, you guys know what pipeline means? Pipeline is it's like when you have when they make cars, they don't make one car entirely and then they finish it. What they do is that some guy does the seat, some guy does the engine, some guy. So it's in a pipeline manner. Same thing happens here. So pipeline here, what we're going to do is that we're going to insert flip-flops in between. So now the adder has 1 T to finish this, and the comparator has another T to finish the job. Okay? So now the adder itself, before the adder plus the comparator was 25 nanoseconds. Now, because I'm inserting another cycle in between, this guy has more time to finish. Okay? So what do? We do the same exact thing. So here, however, we're keeping the same clock cycle. We get the same throughput. So F pipe is equal to F ref. V pipe. Now because this one has more time, I can decrease the supply voltage by 1.7 roughly. Capacitance, C pipe, because of this new flip-flops, is a little bit higher. C ref. So power dissipation of the pipeline data path is this times F ref times V ref, and that's roughly 0.39 of P reference. Okay?
Question.
Yeah.
Why we have more time now? The frequency is the same. Yeah?
The frequency is the same.
Yeah. So why we have more time now? Then we can
Because
lower the voltage.
Before, I had T cycles for the adder and the comparator combined. Now I have T cycles only for the adder and I have T cycles only for the comparator. Do you understand? There is something that, okay, so, you know, there's something called throughput and there's something called latency. Right? If I have a black box, like this factory example, you know, I can have, if I have many working stations, if I have like 10 working stations or 5 working stations or whatever, and each one corresponds to a clock cycle, that if once I insert something here, it takes how many cycles to get